Okay, in this video what I'm going to do is I'm going to briefly describe both the conceptual as well as practical reasons why someone might turn to a Probit or a Logit model to run their regression. Specifically, you run Probit and Logit models under mostly two scenarios. The most common scenario is that you have a binary variable that is either 0 or 1 and never takes any values other than 0 and 1, and you want to have that variable on the left-hand side. For example, a model that tries to predict whether someone has health insurance, or predict whether someone went to college, or predict whether someone has a child, for example. There could be any number of binary dependent variables that you're interested in measuring causal effects. But two things. The first thing is that ordinary least squares is not equipped to handle binary left-hand side variables. Although, if you go to Stata and you try to run a regression with a binary left-hand side variable, Stata will not tell you that that's a problem. So you have to know that in ordinary least squares, you're not able to run models with binary left-hand side variables. The most basic form of a left-hand side variable that is binary is sort of an on-off situation, or like any particular indicator. Equals 0 if the condition is not met, and 1 if the condition is met. These are very common models used in applied economics because there's all sorts of interesting questions in which what you're interested in is not so much an explicit causal effect, but you're interested in the change in likelihood. See, when you have a binary left-hand side variable, what your regression output actually measures is the change in the likelihood that your observations will end up being switched on. In other words, if I run a regression with a binary dependent variable, then the causal effects I'm trying to understand would be effects that specifically alter the likelihood that that event occurs. So for example, if in a model I'm trying to measure the effect of age on whether someone has health insurance, and I run a regression where I have, does someone have health insurance on the left-hand side, a binary, and age on the right-hand side, then what we're literally measuring is the causal effect of someone's age on the probability that they have health insurance. And that's the most unique thing about binary dependent variable models, is that in fact what you're measuring is the causal effect on the likelihood, or a causal effect on the probability that a particular event occurs. Usually in a regression, what you're trying to measure is the marginal effect of one variable on another variable. In other words, if I get an additional year of education, what is the marginal effect on my income? Well, when your left-hand side variable is a binary variable, what you are instead measuring is, for example, what is the change in probability that someone has, for example, insurance relative to their age. Now again, if I have data in Stata with a variable that is binary, and I go and I try to run a normal regression model, what we might call a linear probability model, Stata will not tell me that there's a problem. In fact, everything will look fine. We'll do one here in just a moment. But the problem is that it will ultimately predict changes in probabilities that are not confined to 0 and 1. In other words, if you actually go through and add up all the effects in a linear probability model, you almost always end up measuring more than one, which is of course impossible. The highest that a binary outcome could ever be would be 1. That would be 100%. The lowest it could be would be 0. And so in other words, what the regression model does is it pushes probabilities outside the realm of feasibility. And so again, this is why we can't use ordinary least squares to measure models with binary dependent variables. So the two potential models that we would use if our left-hand side variable was binary would be the Logit model and the Probit model. And the only difference between the two is simply how they assume the The only difference between the Logit and Probit model is the assumption that each model makes of the cumulative density function, or the CDF. The CDF is what we use to estimate, essentially, the potential statistical significance of our underlying regression model. And depending upon the assumptions we make of the cumulative density function, in the Logit case, we assume that the CDF is distributed logistically, and in the Probit model, we assume that the CDF is distributed normally. And just to give you an idea of, sort of what we're discussing here and how close the Logit and Probit models are to each other, let's look at the differences between. So the blue line is the normal CDF, and the red line is the logistic CDF. And the dotted line here is the differences. So you'll notice that the only real difference between the normal CDF and the logistic CDF is around the perceived means. That is to say that they behave differently around, here the mean is 0, they behave differently around the mean than they do otherwise. And specifically, the logistic CDF, again, this is the red one, has heavier tails. So in a way, what the logistic CDF does is allows for greater potential variance around the mean, which from a regression standpoint may mean that the logistic CDF is more robust than the normal CDF. So oftentimes when you run Probit and Logits, you usually check both, with the understanding that the Logit is slightly more robust from a statistical perspective than the Probit model. Okay, so let's go back to our data. Again, the way that this data is, it's cross-sectional data on individuals. I have all of this particular data. And again, what our interest is going to be is to measure the causal effect on whether someone has insurance or not. Again, insurance is going to be our main variable of interest, and it is a binary outcome variable. So let's run our model. Again, we're going to run an OLS model. Again, we know this is wrong, but just so you see that nothing's going to tell you that this is wrong. So we're going to regress INS, and then we'll also do these other variables of interest. Again, whether the person is retired, their age. This variable is a binary variable for whether the person reports their health status as being good. So this is health status as being good. The household income, the number of years of education they received, is the person married, and is the person Hispanic. Okay, so we're going to run this regression, and again, see that we're running a normal OLS regression with a binary dependent variable. As you can see, not only does Stata not tell us there's any particular issue, and we also get a bunch of statistical significance. Now, again, the idea here is not that the OLS regression won't give us some information, and it certainly will. In fact, we'll see in a moment that when we run the Probit and the Logit models, that we get very similar statistical significance, t-statistics, with respect to coefficient estimates. The problem is that normally when you interpret this coefficient estimate, this is the change in the left-hand side variable, this would be insurance, relative to a unit change in this. So, is the person retired has a 0.04 change with respect to does the person have insurance. But that doesn't really make sense, right? There's just no way to interpret that. So a 1 unit change, and whether they're retired or not, this is binary, causes a 0.04 change in whether the person had insurance. As you can see, there's no way to interpret this result, right, through ordinary least squares. It doesn't mean that ordinary least squares won't tell us something about the underlying relationships, but we cannot interpret that coefficient at all. It doesn't tell us anything. So, now what we'll do is we'll run a Probit model. Same model as before. Again, insurance as the dependent variable, and these covariates on the right-hand side. So run that regression. The first thing you'll notice is that, again, because the model uses a log likelihood method, it has to converge. So basically what the log likelihood is that it's finding the specific log likelihood function that corresponds to the sample. and oftentimes it takes a number of iterations before it finds the correct log likelihood function. This is actually pretty quick. It only took 4 iterations. Sometimes this can be thousands of iterations. When I was in graduate school and I was working on my dissertation, I was running Probit models that would take about 12 hours to run. It would usually go through about 10,000 iterations before they found their log likelihood function. So this one obviously converged pretty quickly. Okay, again, you'll notice that if we just compare these results to the ordinary least squares results from above, that the statistical significance is virtually the same. What is significant over here is also significant here. You will notice that the coefficients themselves are much different. But again, we know that the left-hand side here is binary. We also know that the ordinary least squares coefficient estimates are, let's say, inappropriately estimated. So we know that at least that under the Probit model that these coefficient estimates were appropriately estimated. But here's the thing, we still cannot directly interpret this coefficient estimate. In these models, when we actually run the Logit and Probit and we get the initial coefficient estimates, it's important to realize that we're only interpreting the sign here. We cannot interpret the magnitudes. The reason why is because what is being estimated here is a maximum likelihood. And there's nothing directly interpretable about a maximum likelihood. All the maximum likelihood does is tell us whether the probability is assumed to increase, that is predicted to increase relative to covariates, or whether the probability is supposed to decrease relative to particular covariates. So what we have to do is once we run a Probit model, we then have to further refine our results and back out those marginal effects. So before we can actually report a specific marginal effect, we have to use what we call the margins command in Stata. All right, and the command to use this, again, is called the margins command. So now it's important that you run the margins command immediately after you run either the Probit or the Logit. Once you move on to that regression, you can't come back and then run a margins command after that. It has to be immediately afterwards. All right, so here's the command for margins. Let me say a little bit about it. This is just the command itself, margins. This is going to compute these specific margins. dy dx just refers to the marginal change on y estimated from x. The star here just collects, it's going to report all of the marginal effects from my covariates. And again, the covariates in this model were everything highlighted there. Again, this is my dependent variable, and then my covariates were listed there. And so this is going to get the marginal effects from each covariate. And then I have a couple options about how I estimate the marginal effects. Most papers, most research will report the at means. In other words, it's going to tell us the marginal effect that the particular right-hand side variable has on the probability compared to the mean. Okay, so let's run this. Okay, so once it does all of the fitting and everything, now what we see here are nice, directly interpretable results. Specifically, okay, so let's interpret some of these. What this says is that if someone is retired, they have around a 4% higher likelihood that they have health insurance, that they've purchased health insurance. Age is not statistically significant. If someone reports that they're in good health, they're about 7.4% or 7.5% more likely to have health insurance. We see that for every dollar in household income, we get a small marginal change in the probability that someone has health insurance. We see that education has a 2.6 or 2.7% increase in the probability that someone has health insurance. And then the biggest effect, which is perhaps not surprising, we see that being married increases your chances of having health insurance, having purchased health insurance by almost 14%. And it's important to remember that these are, again, relative to the means. So imagine we took the average person in our sample. What this says is that relative to the average, a retired person is about 4.5% more likely to have health insurance. Relative to the average, a married person has almost 14% higher likelihood of having purchased health insurance. If we just leave off the at means option, what it will do is it will compute marginal effects at the marginal individual level. Usually it's almost identical to this, but it can be helpful to do it. So let's run the Probit again. Then we're going to run the margins command, but this time we'll take out the at means option. And as you can see, we get results which are very, very close. This time, instead of comparing or using the average to compute the change in coefficient estimates, now what we're doing is we're using the individual marginal effect. So this is perhaps a little bit more of a refined view, which is why you generally will see that the effects are a little bit smaller. Here, for example, in this we predicted about a 4.5% effect from retirement. Here it's a little bit lower, about 4.2%. Notice that here the married effect is below 13%, whereas here we found that the married effect was actually above 13%. So once we take into consideration some of those individual effects, we see that the overall coefficient estimates are slightly reduced, although we still get really good statistical significance, and they're not reduced by very much. Okay, so now what we're going to do is we're just going to run that same model, but instead of a Probit, we'll run it as Logit. Again, it goes through the same log likelihood iteration technique, and you'll see that the results are very similar. Again, just like the Probit, we cannot directly interpret these Logit results. So again, we use the margins command. And we see we have very, very similar results, all right, to the Probit results. And the last thing that we can do is perhaps, in my opinion, the best aspect of using Probit and Logit models is that you actually can formulate a pretty interesting data visualization called margins plot. So again, let's just run this Logit model. We get these results. Then we'll run the margins command, just like we did before. And we get these results here. Then what we'll do is we will just simply type margins plot. All right, and this spits out a really interesting graph, and here's how you can interpret this graph. This is, 0, so you can imagine here is no effect, all right? And if you look back at the regression results, you'll see that age, for example, was not statistically significant in our model, which is why you see it here at 0. You also see that household income here is reported as 0. Now this is 0 not because of a lack of statistical significance, but this is 0 because the actual effect on household income is virtually 0. So it'll show you not only statistical insignificance, but also those effects that are 0. So you can see that if someone's retired, they have a higher chance of having health insurance. If they report good health, they have a higher chance of having health insurance. The more educated someone is, the higher the likelihood they have health insurance. Married also increases the likelihood of health insurance, and as we can see here, whether someone is Hispanic or not clearly declines in terms of their probability of having health insurance. So one big takeaway from this is that people who report as being Hispanic in the sample, on average, are way less likely to have health insurance, almost 20% less likely to have health insurance among Hispanic individuals compared with non-Hispanic individuals. All right, and we can compute the margins plot for the Probit, so let's do that. Now we'll just do margins plot. Boom. And you'll see it's virtually the same, nearly identical. But again, this just gives you a nice visualization. And what you want to interpret is that if anything's above 0, this means it increases the chances or increases the probability. In this case, increases the probability someone has health insurance. And anything below the line hurts the chances or decreases the probability that someone has health insurance. All right, so that's going to wrap up our discussion on Probit and Logit models. There's a lot of complicated territory to dig in terms of, for example, if you think that your model suffers from a lot of heteroscedasticity, and there's all sorts of like really, kind of complicated statistical issues with Probit and Logits that are not really important for the purposes of this class. What's important is just that you know that you have the potential to run Probit and Logit models, and so whether it's the main variable of interest in your model or the main hypothesis, or whether it's a secondary hypothesis. And I'll give you an example. In one of my chapters of my dissertation, what I was interested in was the effect of rainy day fund usage on U.S. states. So what happened when a state put money into their rainy day fund? Well, what I was also interested in were what were the underlying reasons that a state would adopt a rainy day fund in the first place, because rainy day funds were laws that states created, and I was interested to see, for example, did previous experience with bad fiscal positions increase the likelihood that states would adopt the rainy day fund? And this is exactly what I found. And so in my paper, I ran a Probit model where the left-hand side variable was a binary. Did the state adopt the rainy day fund this year? And then on the right-hand side, I looked at various lagged economic variables, expenditures, revenue, debt, so on and so forth. And what I found is that those variables associated with worse fiscal positions increased the likelihood that a state adopted a rainy day fund. And even though this wasn't the sort of main purpose of the paper, it did add to the overall point of the paper, which was that states had adopted rainy day funds as a means to reduce fiscal consternation. And I could see that by running a Probit model and showing that those states that had fiscal consternation, they were states that adopted rainy day funds first. Right? And that sort of set the stage for me then to later on measure, well, what was the actual effect of rainy day fund usage? So whether it's your baseline model or whether it's just an additional model, Probits and Logits become very interesting ways for us to answer questions that are perhaps not the typical questions that you would ask in a paper. Again, what is the effect of some variable on economic growth? What is the effect of some variable on someone's wage? With Probit and Logits, you're now able to ask questions like, what increases the chances that some event occurs? What decreases the chances that some event occurs? Which, of course, in the context of like policy, if we're talking about, like, imagine that we had a model where you put infant mortality on the left-hand side, and you wanted to measure what were the socioeconomic demographic characteristics that led to higher infant mortality or lower infant mortality, right? It's a very important question to answer, and we could do that. We could uncover some of that if we were to run a Logit or a Probit model.